All right. For number one, block A is on a horizontal surface and block B is on top of block A as shown in figure 1. A horizontal spring of constant K is attached to a wall at one end and block A at the other. Blocks A and B have mass as MA and MB respectively. There is a coefficient of static friction mu S between the two blocks, while the friction between block A and the surface is negligible. Block A is pushed to the left against the spring, compressing the spring, and then released from rest, resulting in simple harmonic motion of the block spring system. The dot in figure 2 represents block B, the one on top, immediately after block A is released from rest. Okay, so the block has been pushed to the side, so the spring is tightly coiled, and then block A is now over here. So the spring is pushing on it in this direction. Okay. On the dot, draw and label all forces, not components exerted on block B, the one on top. Each force must be represented by a distinct arrow starting on and pointing away from the dot. All right, we always have the force of gravity. I'm just going to write mg. And then we have the normal force, which is the force of block A pushing back up. And then, if the spring has been pushed to the left, it's going to want to push to the right on block A, and that in turn is going to push on block B. So there's going to be a force to the right. If you're not sure about this friction force, if you're not sure about that, think about for a second if you were block B, right? And block A has been pushed to the left, and then it's released. It's going to want to accelerate to the right, and block B is going to also want to accelerate to the right as long as there's no slipping. Okay, so there's got to be a push to the right to match the acceleration. So those are all your forces. Notice that Fn and Mg are equal in magnitude because there's no vertical acceleration. Calculate the numerical value for the maximum oscillation amplitude that a block spring system can have such that block B will not slip on block A. So let's visualize what's going on there. So let's say you've got, here's the wall, and we have our equilibrium point, which we'll represent with this dotted line. We're saying how far can we push the block so that when we release it, the block on top doesn't fall. Because the further we push it from the equilibrium point, right, this displacement value x right here, that's our displacement from equilibrium, the further we push it, the more force it's going to exert on block A. Let's clean this up a little bit. Right, it's going to exert on block A, and then if we push too hard on block A, it'll slide out from underneath block B. So there's a maximum force that A can handle and a maximum acceleration that A can have before it slips against block B. So that's going to be limited by this force right here, FF. And FF is basically, let's kind of make this a little thinner, FF is mu times Fn. That's how you calculate the force of friction. All right, so let's keep that in mind. There's some missing information here. Oh, there we go. Nope, we're missing the information. The mass was given in there in mu and everything. I think I forgot to screenshot it. Well, let's just figure it out. Here we go. So, mu was given in the problem as being 0.35. Okay, mu of static friction. That's the coefficient of friction between the two blocks. So that's this value right here. The mass of block A was 5 kilograms, and the mass of block B was 1.5 kilograms. Okay, so we can use that right here, and we know mg is going to be equal to 1.5. Again, this is the free body diagram of block B, free body diagram, block B. 1.5 kilograms times, we'll go with 10 newtons per meter, equals 15 newtons. So that means Fn equals 15 newtons, and that means mu Fn equals 0.35 times 15 newtons, and that ends up being 5.25 newtons. So that is the friction force. Now, that is the maximum friction force that block B can experience before it starts to slip against block A. All right, I'll say that again. That's the maximum friction force that block B can experience before it starts to slip against block A. Now, if we know that that is the force that block B experiences, we can also calculate the maximum acceleration that block B can feel, right? And we can just use Newton's second law. We can say the net force is equal to mass times acceleration, and therefore acceleration equals the net force divided by the mass, right? Just rearrange that equation. And if I said, what is the net force being felt by block B? Well, these forces cancel out, and the net force is simply the 5.25 Newton force to the right. That is the net force experienced by block B when block A is released from rest. So let's calculate that acceleration for block B, right? That would be the net force on block B divided by the mass of block B. Oops, that should be kilograms. And then when we divide those, we get 3.5 meters per second squared as the acceleration of block B. Well, the two blocks are connected to each other, so they would actually have the same acceleration, so that's also the acceleration of block A. Okay? Now, the question was asking, what is the maximum oscillation amplitude? That's this value right here. Well, how is that related to the forces and accelerations? Well, that x value, right, is in Hooke's law, the force of a spring is k times x. So the bigger that stretch, the bigger the force. And the bigger the force, the bigger acceleration. This is where it's tricky, is we can choose to model block A by itself or the AB system. So let's take a look at the two different scenarios. So if we model block A, let's thicken this up a little bit. If we model block A all by itself, right, we've got several forces on it. We've got, we've got mg from block A. Then we also have the force of block B acting down on it, force of block B. And then we have the normal force, the ground pushing back up. And then we have the spring force pushing to the right. And as block A tries to push block B will push back. So we actually have force of static friction from block B pushing on block A. Okay, that's one way we could look at it. A simplified version of the situation would be to look at it as a system. So let's say A, B system. That's the two blocks and the spring acting together. Or just the forces on the two blocks. All right, now we have the mass of the system. So to be clear, I'll put M A plus B times G, right? Then we have a normal force pushing back up. And now we have the spring force, the same spring force, pushing to the side. Now we don't have to model this friction force between the blocks because now that is an internal force. So this is sorry, I forgot to label the normal force. the AB system is a little simpler because you don't end up having to model internal forces, and both of these in red are actually internal forces. I'm sorry, I apologize. If we model block A all by itself, the friction force between the blocks and the force of block B on A, those both end up being extra forces or internal forces, or sorry, external forces. But if we model it as an AB system, now we have a simplified model because we don't have to worry about those forces. They're internal to the system. So what's the bottom line? The only force causing this system to accelerate is Fs, right? These two do not cause acceleration. Acceleration is in the direction to the right. So if we use Newton's second law, again, net force equals mass times acceleration, right? We can actually solve for the maximum force felt by this system. So this would be 5 kilograms plus 1.5 kilograms. That would be the mass of the system, multiplied by the acceleration of the system, which was 3.5 meters per second squared, right? And that ends up being 6.5 times 3.5, right? Whatever that is. Let's just write it as 6.5 times 3.5, and we'll figure that out later. And that is equal to Fs. Why? Because the only force, right, the only force on the spring causing acceleration, probably shouldn't have used green, probably should use red, be consistent. The net force is the spring force. So we can replace net force with Fs. And we can replace Fs with Kx. That's how you calculate the spring force. So we have 6.5 times 3.5, right? Now we're solving for the maximum stretch, x. So that ends up being 6.5 times 3.5 divided by 120 newtons per meter. That's the spring constant. And when you divide all that, you get 0.19 meters. That's the maximum amount the spring can stretch, which would cause a force, whatever these two numbers multiply to be, about 22 newtons or so, right? And that would cause a friction force of 5.225 newtons between the blocks, and that's how you're maxed out.